Okay, here we go. I'm just trying to figure out my stupid Zoom windows. All right, so let's take a look at what equation you start with. We're starting with this same one, the end result, which is what we're actually in the end after, right, is equal to the starting value times e to the r, or sorry, kt. And we'll just start filling in when we know. In fact, I'm going to write it on the left side of the things that we're given. So we're given the starting value of a naught is equal to 10. We're also actually given the ending value a is equal to 600, right? E is just it's a number, so we don't have to bother with e. That's not a variable. K is we don't know, but we know time is equal to 30 days. Yeah, before from 10 starting position to 600, it took 30 days. So we're just gonna fill all those things out. 600. Let's use a different color since I started that in blue already. So 600 is equal to 10 times e to the k times 30. Right? Or let me write it like 30k. 600 is equal to 10 e to the 30k. All right, so now there's only one letter, right? Everything else is a number, so I can solve for that letter. And the way we solve it is the same way we've been solving these sort of questions. We just use the log functions. But first we need to get this by itself. So divide both sides by 10. I get 60 is equal to e to the 30k. And then now I can just natural log both sides of that. So I'm going to natural log this side, natural log this side. When I natural log the right side, it undoes the thing. So I end up with just natural log of 60 is equal to 30k. Right? And so then I can divide by 30 to get my answer for k. So divide by 30. On this side, I'm going to end up with k. And divide by 30 on that side, I end up with ln of 60 over 30. This is my k, right? ln 60 over 30, whatever that is. At this point, if you want to, you can just make a decimal approximation, or we can leave it like that. Let's just take the decimal approximation because I think that will be easier for you guys to follow. All right, so k then is equal to about, roughly, plugging this into my calculator, 0.136478. And you want to leave a good number of decimals just so that you don't lose too much accuracy when you plug the thing in. So this is what I was saying earlier, right? We just plug all the numbers we're given until we solve for the one that's missing. But then we haven't actually answered the question because the question did not ask for what's the growth rate. It asked for what's it going to end up with the population after 30 days or 30 more days. But 30 more days means actually 60 days, right? From the starting time is 0. 30 days later was 600. Another 30 days would be 60 from the starting position. So let's just write all our variables here. This time a is the thing we don't know. We know a naught is still 10. K we just figured out is 0.136478. And time is the thing that is now 60 because it's 30 days plus 30 more days. And so now I have everything except for one, right? So let's look again at my equation. I have all the variables except for a, so I just fill in all these numbers and then see what I get. So this is going to be, let's do this in red again. So a is equal to 10 e to the 0.136478 times 30. And I just plug that into my calculator to see. Be a equal to something. So e to the, and if you're not sure where the e function is, again, it's the e to the x, or if you're using the iPhone calculator, which I actually recommend you to do not this iPhone calculator because it's hard to see, but you can find it. It's the E button when you turn your calculator sideways. 1, 3, 6, 4, 7, 8. That's the exponent times 10. Oops. 3, 6, 4, 7, 8 times 30. Can I get, oh, I'm sorry, 60. I tipped the wrong thing. And then let's just round to the nearest whole, whole number. Okay, so here, if you guys can you see my calculator? I actually did it twice. I did it using 30, and not, first time was a mistake because I forgot to change to 60. But if you look, if I do plug in 30, then it gives me what I expected, right? It gives me right about 600, 599.99. That's what it was supposed to be at 30 days, right? It's supposed to go from 10 to 600. So that just confirms that I have the right value. And now if I plug in 60, it's instead at 35,999. So about 36,000 to the nearest whole person. So we're just going to round to 36,000. So since I'm making an approximation, I'm just going to write about 36,000. Okay, so this is how you would use exponent, and you know, a lot of populations do in fact grow exponentially, but then they don't stay exponential forever because you have limitations, right? Like, for example, one limitation would be just the total number of people. Like once you hit the total number of people, and it would be impossible for it to grow past that and continue to grow, keep growing. Or there are other limitations, like think about like wolf populations or something. Wolf populations, they're gonna be limited by how many bunnies they can eat or whatever it is. Yeah, but here's a model anyways. This is one form of model. So using this model, we'd expect 36,000 cases after 60 days. But again, don't be too alarmed because this is far from a perfect model. And this is like way below what is actually probably happening. I mean, way above. Okay, that's the first question. Any questions about the first question?
I just have a question. How to use the calculator? Do you just hit 10 and then do Shift E? Because then I'm getting like a way lower number.
Okay, which calculator are you using? Because that makes a difference.
I'm just using like one of those Texas Instrument.
Okay. So in that case, we should be okay. Like mine, this is a TI emulator. So you just write 10 and then multiplied. So times by 10 and then e to the whatever power. Just make sure your exponent is in, if it's like, for mine, it gives a separate environment for the exponent. So you can just plug it in directly like that. Or if it doesn't give you that, then make sure that you have parentheses for the exponent, because otherwise it's going to take the first number to that power, but it's not going to include the times 30. It's going to multiply by 30 afterwards. Because exponents come before multiplication, right?
Right.
Yeah, so you want to keep your exponent in its own set of parentheses.
Makes sense. All right.
Okay. Let's see if you get that 36,000.
Oh yeah, the problem was that I wasn't having it in the same parentheses.
Okay, right on. No problem at all. It's a very common thing. You're not alone. Okay, number 2. A biologist has 100 grams of radioactive substance. After 1 hour, she only has 12.5 grams. What is the half-life, the amount of time it takes for the substance to dissipate to half the original amount? This is kind of what we were talking about when I was showing you the pictures. So exponential growth and decay, like when you're talking about this kind of things, the carbon dating kind of thing, right? Where they have some radioactive substance that loses half of itself every certain time period. And both of these use the same model. A is equal to A naught e to the RT. Okay, so what are we given here? We're given that she started with 100 grams, right? So your original starting value is 100 grams. You're also given after 1 hour, she only has 12.5 grams. So you're given A is equal to 12.5. You're given, oh, I keep writing R for rate, but which I think makes sense, right? R stands for rate, but we're using K in our book, so K is also common. So. Okay, K is a thing that we don't know, right? We don't know what K is. We do know the time though is 1 hour, so time is just 1. Keep in mind that's 1 hour we're thinking about. And so the first thing we want to do is figure out what K is, because that's the one thing that's missing. So I'll write everything in. 12.5 is equal to 100 e to the K I don't know, and T is just 1. Okay, so I'm going to solve this now for the one letter that I don't know. Okay. I'm just going to alternate between red and black this time. So same like before, going to divide both sides by 100, right? Divide by 100. I don't know why I wrote this out. I rarely write that out, but I don't know, I did just now. So divide by 100, you're going to get 0.125, right? Because I just moved the decimal twice, is equal to e to the K times 1 is just K. So e to the K. And then, as usual, I'm going to take ln of both sides. Oops, that's not an exponent. It's ln of this. It's ln of that. On the left, it's going to give me ln of 0.125. On the right side, the ln undoes the e, so it's just equal to K. So K is equal to ln of 0.125. Let's write that as an approximation. So ln of 0.125 is negative 2.079. Okay, so K is roughly negative 2.07944. Let's round to that far. Negative 2.07944. Okay. So now that I have my K, I'm going to come back to make sure we're answering the question. The question did not ask for the rate. It asked for the time, the half-life. How much time does it take for a substance to half? Well, that means, okay, let's write our variables again. How do I get from starting position to a half? A half would be 50, right? A naught, if I'm starting from 100, a half would be just half of that, so 50. K I know now is negative 2.079442. And time is what I'm trying to figure out. How long does it take to reach from 100, exactly half of that? So I just plug these values in. Here's my equation again. And just plug in all the values I know this time. So 50 is equal to 100 e to the negative 2.079442 times t. Okay, so divide both sides by 100, and I'm going to get 1/2 is equal to e to that negative 2.079442 times t. Again, I take ln on both sides. And on the left side, it gives me ln of 1/2. And on the right side, it gives me just negative 2.079442t. So I divide both sides by this value, and I get t is equal to ln of 1/2 divided by that thing. Okay, I'm out of space here, so let me write smaller. So ln of 1/2 divided by negative 2.079442 is equal to t. Let me plug this in. Okay, and I get roughly 0.33333. Yeah. So it's basically about a third of an hour, a third of 1 hour. Or you can think of that as being about 20 minutes. Yeah. Let me write that up. So 0.3, let's just go to 4 decimal places. So 0.3333 hours. Remember, time was in hours, right? So hours. In fact, it turns out that if you write the true value, the exact ln of 0.25 instead, you divide that, then you're actually going to end up with exactly 1/3. So exactly 1/3, which is 20 minutes. It takes about 20 minutes for her thing to happen. Okay, guys, I'm going to stop this video now, and then we're going to talk about the last 2 questions.